It's interesting stuff. It was happening really long and
All right, let's start on page 12. We did page 11 already. So let's go to page 12. The graph consists of line segments. Find G prime and G double prime. So right now, F is sitting at a level above G. So if we want to find G prime, then G prime is simply asking for the derivative of this notation. Which second theorem is just going to drag this level down to f of x times 1, which is just f of x. And then likewise, if I want to find G double prime, then I'm making G prime drop a derivative level down. So I'm also going to let the right side drop one derivative down. Part C and D, you're asked to find G of 4, G of -2. That's going to be built off of the G of X function, which is going to require us to involve area or displacement under our region between the graph and the x-axis. But just be careful here because you may see all these different shapes. That's not part of our diagram. You may see a triangle here. You may see another triangle here, another triangle here. And so I would start off by shading in the region that you're concerned about, right? Because if you accidentally start looking at regions outside the interval, outside these regions, then all your numbers that you're finding is going to be off. So let's start off by shading. You're only looking at what's between the graph and the x-axis, and that's it. You may see a triangle here, another triangle here, another triangle here, but if it's not part of your shaded region, it's not part of your problem. Okay, so we see a collection of triangles and squares and rectangles. So let's go ahead and find all those regions. Triangle is 1/2 base times height. Okay. Zoom in. All right, so find G of 4, we see that it's going to be using our original definition. So replace the x with 4. So the bounds are in the order that we would like: smaller value to larger value, lower limit, upper limit. So we're reading from left to right. So all the positive and negatives are going to be what we would expect. So 2 to 4, we have positive 1/2 plus 1, so 1.5. Find g of -2. Follow what the rule tells you. And if you look, we're going from 2 to -2. We're going backwards here. Now, if you're comfortable with just adding or changing all these numbers in your head to the opposite sign, then that's fine. But I'm going to rewrite the bounds from smaller to larger and then pulling the negative out in front. I'm going to focus on gathering the value in that region, and then whatever number I get, whatever number I sum up to, I can just change the sign at the end. So -2 to 2 is going to be 1 plus 1/2 minus 1/2 minus 1/2. So 1 minus 1/2, because the 1/2 cancels out. So 1 minus 1/2 is 1/2. But there's a change in sign, so I'm going to put a negative in front. Part E is asking for G double prime of -3.5. So if you look, G double prime is defined as F prime. F prime is asking for the derivative or the slope at -3.5. So I'm going to highlight that point here. We're not asking for the point here. We're asking for the slope that this line is part of. I can just do rise over run. Let me add one more here. What if I asked you to find G prime of 1? So we find our definition here. G prime is related to F. So G prime of 1 would be F of 1. And F of 1 would just be the order pair on this F graph. So F of 1 would be -1. Any questions so far? Part F, for what values of X is G increasing? So let's make sure that we understand this is not the G graph. So we can't just say, oh, G is increasing in this interval, G is increasing in this interval. This is the G prime graph. So let's make sure we understand this is the G prime graph, not the G. So you're basically looking at the derivative graph. So we can label accordingly, make sure we understand what we're looking at. We're looking at something that's describing not the location of our G graph, but the slope of our G graph. So anything above is positive slope, anything below is negative slope, anything on the x-axis is slope 0. So we start off, let's build our G prime sign line. First, by locating your x-intercepts, so -3, 0, and 3, and then endpoints from -4 to 4. Let me try that again. All right, so between -4 and -3, we clearly see below the x-axis. So that's going to translate to a negative slope. Between -3 and 0, above the x-axis, so positive slope. Between 0 and 2, negative slope. Between 2 and 4, positive slope. So G is increasing, so the arrows are going to be a lot more helpful in terms of help seeing where our graph is actually increasing. So basically, wherever the graph is above the x-axis, right? So from -3 to 0, and then from 2 to 4. Okay, for what value is G prime decreasing? So this is my G prime graph, right? So G prime decreasing. Now we can look at the slope, right? So G prime is decreasing in this interval. So this is basically asking about when is the graph going to be concave down? So G prime is decreasing because G double prime, or basically the slope of my G prime graph, is less than 0. I have a negative slope on my G prime for my G prime. Find the absolute extrema. So absolute extrema, we have to think about extreme value theorem. So we're going to test endpoints and critical points, and you're just going to pull your candidates from your G prime. If you have a G double prime sign line, those critical points don't matter. Okay, it's just purely off of your G prime. So it looks like we're going to test 2 endpoints and all the critical points because these are all relative max and mins, and so these are all valid candidates for absolute max or absolute min. So we'll need to find G of -4, find G of -3, find G of 0, find G of 2, find G of 4. We have some of the data that we need from part C and D, but we need to gather more information. So we're going to test all these points here. Now, if some of these did not have a change in signs, then we wouldn't have to test those critical points. But these all have change in signs. And it's not just asking for max or min, it's asking for absolute extrema. So both max and mins. Oh, sorry. My bad. It's only asking us from -1 to 3. So we don't have to go as far left and right as I had it. So we're just going to test -1, 0, 2, and 3. Right? Sorry. We're looking at the intervals here, so no need to look at -3, -4, or 4. So let me start off with my first endpoint, G of -1. So G of -1, did not get that from my original from above. So we're going to go back to our definition and build it from scratch. So G of -1 will be from integral from 2 to -1. Follow what the rule says. Again, I would like to read my graph from left to right, so I'm going to change the bounds. So -1 to 2. ½ minus ½ is 0. 0 minus ½ is -1/2. So negative or -1/2 would be +1/2. Next up, G of 0. That's a critical point now that we want to use. So that's from 2 to 0. Right, the bounds are still out of order, so I'm going to flip them and pull a negative outside. So 0 to 2. That's a negative 1/2 minus 1/2, so that's negative 1. But we're changing the signs here, right? So negative of a negative 1 will be a positive 1. Let's test 2 as well. All right, so 2 is easy because the bounds are going to match. If the bounds match, that means I have no area for me to find. That's just going to be 0. All right, G of 3. Integral from 2 to 3. This is also doesn't require any adjustments. We can just keep it because 2 is less than 3. This is going from left to right. So 2 to 3 is 1/2. Right, so our end goal here is to identify the highest and lowest y values. We don't really care about the x value location, just the y value. So the highest, largest number we see is a 1. That's my absolute max, and my absolute min is 0.
You test G of 1.
Did I not test G? Oh, I didn't test G of 1 because it didn't show up in my sign line. So, I mean, you could, but you're, I would say just do what you see in between. Or just do what you see in your candidates list. Three was not on the sign line because it was not a critical point from our G prime sign line. Right? Remember, critical points is only going to come from your x-intercepts. So that's how we built our sign line here. You know, we weren't using every integer value, right? We're pulling that from our sign line. These are the only max and mins that we pulled from our sign line. Okay, any questions there? All right, so, you know, don't assume that it's just, every integer value needs to be tested. You know, it could be, this could have been landing at a decimal value or a fractional value. If it were, then we would have to test it. It all comes from your slope sign line. It all comes from your x-intercepts. If there's a change in signs with your x-intercept, then that is a relative max or relative min that needs to be used as a candidate for your absolute max or absolute min. Okay, absolute max is 1, and absolute min value is 0. So I'm going to be looking to see that you're choosing numbers from your candidates list. Okay, so it needs to be coming from this list. Otherwise, you're just grabbing a bunch of numbers that with no connection to your slope sign line. Right, any questions here? Next up, the following table shows the size of an incoming wave headed towards shore at a given moment. Use the trapezoid sum with 6 subintervals. Let me change this here. let me do three. So I think, yeah, let me do 3 subintervals. There's something that I want to show you with 3 subintervals that can get lost with 6. So let's do 3 subintervals from 0 to 53. So we'll do one that's here. Next one here. Next one here. Now remember, trapezoid area is 1/2 width, height 1 plus height 2. Make sure we memorize that formula. It's basically a triangle, and then you're adding another height. The width is subtracting where those intervals are starting and ending. So 18 minus 0 is 18. 36 minus 18 is also 18. 53. Okay. Now, with trapezoids, you're only adding 2 heights. So make sure, the reason that I want to do this is I wanted to make sure that I see some students do this where they want to add up all the heights they see, 0 plus 5 plus 13, but the formula only asks you for 2, and you're only going to be using the 2 that the ends are pointing at. And then you're pulling your heights from your second row, right? So essentially, we are approximating the depth integral, right? We're approximating the depth integral from 0 to 53 using trapezoids. And what is our units going to be? Yeah, feet squared. Good. So remember, anytime, whatever function we start off with, if we're taking the antiderivative, it's going to have to change its units. Essentially, you're multiplying. If you're multiplying all these numbers, width and height together, then you're also multiplying your units together. So this is now going to be feet squared. Okay, let's do 3 middle rectangles. Sorry, that's the wording got cut off there. But now middle rectangles, looks like the interval has already been split up the way that we did for part A. And then now you're just picking off the height in the middle. So these are both trying to approximate the same thing, but The trapezoid is going to be the better approximation of the two, but you're not going to be asked to compare. But just to let you know, trapezoids are geometrically is the best approximation. Okay, average height. So this is average value theorem, right? So 1 over b minus a, integral from a to b of h of x dx. Okay, we're going to be using part B. So So 514 divided by 53. It'll be different from the key because we changed this to 6 from 6 to 3 trapezoids. So you're starting with feet squared. You're dividing by feet. So now you're back down to feet. Oh, sorry. I was looking at part. For some reason, I thought this was part B. Okay, sorry. 677 divided by 53. Thanks. Yeah, feet squared divided by feet, we're back down to feet. So if we were to average out all these different heights, our approximated average height is 12.7. And that should make sense, right? You look at all these heights. If you just do a quick visual, 12 lands somewhere between 0 and 26. So that seems to be a reasonable average height. Let's see. Okay, I don't have another particle motion for us, but maybe I can just walk through page 11 again, just so you feel comfortable with all the keystrokes that we're doing here. And again, I'm going to leave all that on the board there so that you have access to that information. So this is page 11. We started off by building our velocity function and then using second trace 0 to find our x-intercepts. And then we used second trace max and min to find our max and mins of our graph, and those will be where acceleration will be 0. To find velocity, we can just plug the number directly into the function, or you can use alpha trace to speed up that process where it'll just plug in for you. Acceleration is the derivative of velocity, and we're going to use math 8, use the n derivative feature, make the calculator find the acceleration value for you, and indicate the notation here. So don't say y1 of 4. Indicate the name of the function. So v of 4 for velocity. You can either say v prime of 4 or a of 4, but don't say y prime of 4 because that doesn't connect with the variables that we have, right? So don't use y sub 1 or y sub 2 on paper because that's just some random notation that the calculators use. Careful with your units of measure. It's not always inches per second. It's going to be indicated in the problem. So if it's centimeters per hour or if it's kilometers per minute, right? Read the problem to see what your units are going to be off. It's going to be. Is the object speed increasing or decreasing? So we compare our velocity and acceleration. If we have same signs, then speed is increasing. If we have different signs, if one is positive and the other is negative, then speed is decreasing. And make sure that you are naming the function you're comparing. Total displacement is just the depth integral from lower bound to upper bound of v of t. So I want to see that v of t notation, as well as plugging in and finding your numeric value. Displacement is not going to be inches per second because we are taking the antiderivative of velocity. So we're transforming it to something at the position level. So it's going to be in terms of inches. Total distance is also in terms of inches. The notation for total distance is the depth integral, absolute value of v of t. Make sure your absolute value is just between the velocity and not outside the integrals. I'm looking for this notation as well as your ability to plug in and finding your answer. Part J, this is asking for a physical location after the object has moved for 11 seconds. We're using this formula there. X of b equals x of a plus the integral from a to b of v of b dt. I'm looking for this notation and the setup. So x of b is my final destination. X of 0 is where I'm starting. And then my displacement is how much progress is this object going to make in that time interval. So this just happens to be the same interval as the previous problem. So you could just grab the same number as before. But if it's different, then you're going to plug this in the calculator on its own and then add that to your starting location. And that will give you your ending location. And average velocity is just average value theorem. Okay, I'm jumping around between different worksheets here. This is the worksheet that we did yesterday. I think we just did 1, 2, and 3. Can we do number 4 on this handout from yesterday? Does everyone not have this sheet? Let's try number 4 here. This is interpreting Riemann sums. Okay, water is pumped into a tank at a rate modeled by R of t, liters per hour, where R is differentiable and decreasing. Selected values of R of t are shown. At time t equals 0, 5,000 liters of water are in the tank. So these are all in terms of liters per hour. But we want to find the depth integral of R of t. So keep in mind, you're essentially turning a derivative to something at the function level. So you know your units are going to change. This is no longer in terms of liters per hour. This will transform into what? In terms of what? just liters, right? Another way to think about it is that you're multiplying, right? This is area related. So not only are you doing multiplication with your numbers, with your width and height, you're also multiplying your units. So now this is going to tell us if we accumulate all these liters per hour over this 8-hour period, we're going to be told, we're going to be able to know how much actual water has been pumped into the tank in terms of liters over this 8-hour period. So again, just be aware of how tempting it is to want to hold on to liters per hour, because students see RFT, they see liters per hour, and they feel like they have to hold on to that unit. But the integral is ultimately changing what this problem represents. So now estimate using Riemann sums. Left Riemann sums. So, it doesn't specify the number of intervals, so that just indicates you're going to use every subinterval you see. So every order pair will have its own subinterval. So subtract your t-values to get your width. And then for each subinterval, you're picking off the height, the left y value. So if we accumulate all these liters per hour over time, we're going to actually be able to know how much water has been added to the tank. So 17,300 liters. How many liters are actually in the tank, though, after 8 hours? Well, there's actually 5,000 to begin with already in the tank before water gets pumped into the tank. So we just add these numbers together. 5,000 plus 17,000, 22,000. Okay, let's do another derivative graph. Have you guys done either page 3 or page 4 off of the test review? Okay, all right, let's do page 4. It's the same process. So I would start off by building out your H prime and H double prime. Let's get those all lined up, because then we can refer to them as we go through our problem here. So if f is sitting at a level above h, then h prime is going to turn that integral of f to f, and h prime would just be f. H double prime would just be f prime. Go ahead and fill out all your area regions. Below is negative, above is positive. And again, you're only looking at what's between the graph and the x-axis. So you may want to start off by shading your the regions so that you're not getting thrown off by other shapes that may appear. Okay, so h of 0 is the integral from 6 to 0 of f of t dt. And if we follow the rule here, the 0 is up above, but we want to read the graph from left to right, and it just feels out of order. So we can go ahead and change the bounds, flip the sign in front with a negative, and now we can add up these numbers that as we see. So 2 plus 2 plus 2, 6 minus 1/2 is 5.5, but we flip the bounds and pull the negative outside, so that 5.5 will turn into a negative 5.5. Any questions there with part A? Part B, h of 6. Well, upper bound 6 and lower bound 6 are going to be the same number, so there's no width. Width is 0, so my area is also going to be 0. H of 10, going from 6 to 10. So 6 to 10, just the two triangles below the x-axis, so -4. H of 11, we're going from 6 to 11, so it's the two triangle below the x-axis and the triangle above the x-axis. So -4 plus 1/2 is -3.5. H prime of 3 is defined as f of 3. We define that at the top of the page here. So f of 3 is just the order pair. F of 3 is 2. H double prime of 9.5 is defined as f prime of 9.5. We're looking at the f graph. F prime is the slope, so we just find 9.5 on our graph. And then just realize as part of this line segment, sorry, over here. And then just find the slope. Slope is going to be up 2 over 2, so slope is 1. Part G, for what value is h increasing? We want to create our slope sign line. This will do two purposes for us. It'll help us answer this question, but it'll also help us give us candidates for our next part for extreme value theorem. So label your graph accordingly here. Above the x-axis is a positive slope. Remember, this is not h graph, this is h prime. Below the x-axis is the negative slope for h, and on the x-axis is slope 0. So pick off your x-intercepts, 1, 6, and 10. Initially, h prime starts below the x-axis, so negative slope. Then it's above the x-axis from 1 to 6, and then below the x-axis, and then above the x-axis. So H is increasing from 1 to 6 and from 10 to 11 because H prime is greater than 0. And then H prime is decreasing. So this is H prime. So H prime decreasing. Now we can look at the slope, decreasing from 4 to 8. And then these are your candidates for extreme value theorem. Okay, so we're not just testing every number between 0 and 11. I want to see that you're testing the numbers that are coming from your candidate list. So we need to find H of 0, find H of 1, find H of 6, 10, and 11. And the nice thing here is that it's all, we found all those from above, so we can just carry all those numbers down. Okay, so then between all these numbers here, we're looking for the highest Y value. So the highest Y value is 0, and the lowest Y value is -6. You don't have to specify the location. I'm looking for the Y values. Just tell me what the Y values are. Okay, let me know if you have any questions, if you have any issues with calculator, keystrokes.
Yeah, I know. Yeah, really. It was crazy. It was more comfortable. Like, yeah, it was like, I was like, I think the best chapter. I see him. I like. I'm like, Thank you.
See you guys next.
Oh my God. How long do you think we spent, like, an hour, like an hour? I think like, 8 points.